So we're getting close to the end of my lecture material. There's this one and then one on practical aspects of computer vision in an industrial setting. So the things you have to think about in order to make a camera system and the software around that. And then we should be in a position to spend all the time doing mini project things. I've had one mini project request in from one of you and not a sausage from anybody else. So can I ask that by Thursday you've all thought about what you want to do and by Thursday you do you let me know what you're interested in doing. I hope to complete the theory side by Thursday halfway through, and from then on Thursday practical will be using the OWL robots. So I need to make sure that everybody who's signing out an OWL robot has got one and that they're here, and that we can then go through the setup procedure to use them within the laboratory. Okay? So I just want to talk about stereo now, and I'll be using some of these terms that you need to become familiar with. Epipolar geometry, I'll mention these as we go through the lecture. Homography, which is a mapping of 2D points onto a plane in a 2D camera. So generally you would do this with several 2D cameras and establish a homography between both cameras. Rectification allows both cameras to be rotated from their actual plane in the 3D world to as if they were parallel and on the same baseline. And the essential matrix and the fundamental matrix both represent rotational, translation and scale factors for the different parameters that can vary between cameras. So, I've gone through some of this last time I recall. We have some target, and it's convenient to use a checkerboard, which we take a left picture and a right picture. Those are rotated and skewed in some way between the left and the right camera, simply because we have not been able to organize them to be perfectly parallel and the lens to be perfectly situated over the sensor. The lens optics and the positioning of the sensor need to be corrected for, and we can do that by comparing the left picture with the right picture and linearizing the what we know to be corners in each camera in isolation, so that we can correct for any geometric distortions in each camera. Once we've done the correction for geometric distortions, we can then rectify the two images in our stereo pair. This rectification allows us to be able to project onto the left array and the right array of data. The same row in the left picture corresponds to the same field of view on the right picture. So if I'm the stereo camera and I'm looking straight ahead and I've had my lens distortions corrected and our eyes toe in automatically, but if I'm focused at infinity, they are perfectly parallel. And then down here on the baseline, I want to make sure that all of the pixels that are on the left camera map in some way to the pixels in the right camera. Now, of course, the field of view is going to be different, so there are going to be changes, but there will be parts of the left camera and parts of the right camera that actually are showing the same scene, because that's the whole purpose of stereo processing. So the rectification process shifts and scales things so that they're perfectly aligned. So for argument's sake, let's say we've rectified the picture such that we can regenerate the entire checkerboard. Now, this is not guaranteed. This depends upon how you do the calibration process. But let's assume you get the entire field of view of the checkerboard. Then the left picture, every single row of data in the left picture will be corresponding to the same point of view in the right picture, and there will, the points that share the stereo disparity, which the stereo view, which will be the left-hand parts of the right picture and the right-hand parts of the left picture, are guaranteed to be on the same row. So you don't have to search for matching pixels, which is the idea in stereo. So when you've done that, you then crop around the area of interest that you know is in calibration, and then you work within those bounds. After having gone through the calibration process, which involves taking up to 20 stereo pairs with the left and the right camera, saving those to your hard drive in some way, storing the calibration matrices in XML, which is what these OpenCV calibration functions do anyway. You then run that piece of, you then run the cameras live. You read in the essential and the fundamental matrices, use those to undistort and to rectify the current pictures that you are taking with those cameras. The cropping then takes place, and then you can do the matching between the left and the right pictures. And remember, the matching depends on distance. So the amount that a target shifts between the left and the right eye depends on how far away it is. If it's at infinity, there is no difference between the location in the X coordinate on the left camera and the X coordinate in the right camera. But closer and closer in, there's a shift that's due to the different views of the cameras and the optics. So you see the curve of disparity, the offset between the X and the Y location for the same feature, drops off exponentially with distance. So for very close objects there's a huge disparity, and for far away objects there's not much disparity. So you can see here, sorry, that's high disparity, low disparity. High distance is a low disparity, so that's a big disparity, and here's a target that's close by and it has a large disparity. Here's a target that's further away and it has a higher disparity, and that has an even higher disparity. And at infinity, where you're looking at the moon, for example, then there's hardly any disparity between the left and the right picture, and it will be down to the pixel resolution of the cameras and the accuracy of the maths during the calibration process. So we're going to be doing this with the OWL. And the principle is to establish the camera orientation. So with the OWL we can move the eyes in X and Y directions independently. So we have to manually put the cameras in as good as we can get for pointing forwards, and that both images are upright and reasonably aligned with each other. You're allowed to have toe in, so you're allowed the cameras to be toed in, pointing towards some target in the moderate to near field. If you have too much toe in, then the common area of overlap between the two pictures is very tiny, and so it's very difficult to work. Whereas if you have the toe in a bit further away, then you get more of a common area between the two camera pictures. So you're allowed to have the cameras perfectly parallel at right angles to the back plane, or toed in by some moderate amount, not too much. You're not allowed to have the cameras toed out, so they can't be looking at two different views, because you will never gain a stereo correspondence between two images that have different views. So the cameras are notionally parallel, and if you remember from David Marr, we're matching on continuity, so we're looking for little runs of pixels that have the same texture, the same sort of variation in grey level slope, uniqueness, that we match colour for colour, grey level for grey level, and the assumption there is that the lighting is even across both camera views, and we're also looking for similarity. So the idea being that the two cameras are corrected to be on the same baseline, and that the distance to the centre of the baseline can be estimated by the difference in location on the camera plane of the pixels of the target. Epipolar geometry is a technique developed by a chap called Zisserman from Oxford that creates a virtual plane, which is here, that a target will project to, and the cameras have some pose in relation to this back plane, and where the projections cross, you have a series of epipoles which are the relationship between the left and the right projective plane, and the epipolar line that joins them is the line that you search when looking for a correspondence. We do this geometric analysis because, having made this calibration, there's an assumption that we don't move the eyes. So the eyes are fixed on some backplane, and if you look at passive stereo cameras, they're all cameras fixed to some metal bar that points them forwards and doesn't move them. And the reason for doing this is that it saves search time, because you only have to search, once you know what that line is, you only have to search along that line to find a match between the two cameras. And the order is preserved, so something to the left of a point in the left camera will be also to the left of a point in the right camera. So that correspondence makes searching very easy. But of course, if you think about it, these cameras could be pointing all over the place. So if you don't do this, then you've got no clue about where to search in the cameras to find out the correspondence. So this is an important step in the analysis of stereo pairs. Distance is simply related to the baseline, and then the accuracy of the number of pixels in the camera between the left and the right picture. So in other words, if 1 pixel is 1/640th of this view, then you're going to get a different error to if it's 1024th of that view. There's a nice master's thesis by, or paper based on this, by Morovle and Vracek in 2008 that is worth looking up if you're going to do any serious work on stereo. They measured the distance of 1 pixel error based upon targets at 10 meters and 50 meters, and you can see here, this is the baseline, so this is the separation between cameras. So if the camera was at 0.2 of a meter and the marker at 10 was supposed to be at 10, but in different parts of the field of view, it was actually measured by the disparity method to be 10.81, 10.58, 10.01 and 10.34. If the baseline was 0.7 of a meter, so there's a bigger separation, then the accuracy improves 10.18, 9.84, 9.96, 10.13. And you can see the same for marker at 50 meters as well. But here, the marker at 50 meters, oh here we are, 50.7, 57.73, 47.38, 46, and with 0.7, so with a wider baseline, you get 52.3, so there's smaller errors. And in fact, there's an error surface. You can actually find an optimal baseline for a given measurement of distance. And this is something that you would routinely set up if you were doing stereo photography and stereogrammetry for analysing three-dimensional scenes. There are two calibration processes that have been developed that are proven to be robust and are adopted by the community. One is Hartley's algorithm, which uses 7 or more points. It operates on uncalibrated cameras, so you don't need to bother about calibrating them. And you call it by saying stereo rectify uncalibrated. I think that's available under version 3.3. And the other one is Bourget's algorithm. So Hartley's algorithm just rotates one camera. It keeps the other one camera fixed, and then successively through software affine transformation rotates the other camera until it minimizes the error between the two cameras, and that is then the calibration matrix. Bourget's algorithm rotates both cameras, so it attempts to find a common ground by moving both cameras in succession. So if both cameras are sort of like that, it's trying to reproject them both onto a common background. And this is called stereo rectify. I think Bourget's algorithm is preferred. It does require you to have calibrated cameras in the first place. So it's looking to minimize, it's not trying to analyze for camera distortions as well. These are both successive approximation methods that use algebra to solve their solutions, and they're not guaranteed to converge to a solution. You can have the cameras, I've noticed, especially if they're towed out, these won't converge to a sensible solution, or if one camera image is twisted too much compared to the other camera image, then these will not converge to an algorithm. Converge to a solution. Once this calibration has been run, you can then save the results in a lookup table, which is on a per pixel basis. So for every pixel from the incoming video stream, you know its XY position, and you know where it reprojects to in the calibrated picture. It's just a lookup table, and the lookup table just contains the signed offset of that pixel. So if it was 0, 0, and it now moves to +2 minus 1, then that means it goes to 2 in the x-axis and -1 in the y, so it disappears from view. And hopefully there's a pixel that replaces that one. So these tables hold the positions of the calibrated cameras, and it's very fast, but the lookup table is necessarily larger than the number of pixels, because you want to be able to calculate the pixel resolution to sub-pixel accuracy. The reason for this is that you don't want holes in your mapping when you do the transformations through rounding errors on your arithmetic. So there's a function called init_rectify_map, which follows the calibration to create the rectified map, and then you use remap. Each time you grab another stereo pair, you use remap to correct those and then do some subsequent processing with them. On a fast computer with VGA cameras, it has minimal impact on the processing speed. So we've got calibrated cameras, we now have them on common baseline, and we have rectified the pictures, so the only pixels we see are guaranteed to have some geometric correspondence between the views. We now have to match patches in the left picture with patches in the right picture. The most robust algorithms use small patches. Stefano et al. In 2002 developed a square patch using a 16 by 16 patch, but it can be any any size really. It has a problem with homogeneous regions, as most stereo matching algorithms do, because if you're thinking about it, if both of your cameras are looking at this section of the picture projected on the screen, you can both of your cameras can see a number of different coloured pixels in here. So the left view and the right view will be shifted very clearly. But if you're trying to detect some pixel differences in this white patch over here, there's not enough information, so you can't do a mapping over here. So stereo depth only works, passive stereo depth only works if you have textural differences in the patches in the picture in the field of view. So trying to do a stereo depth of this wall here will give you strong answers for where the text, strong answers for where you have features, and no answers, so holes where there is uniformity. This then leads to lots of gaps in your data, so stereo pictures look quite noisy. The area-based scheme can work nicely with colour, but occlusions between objects, so if there's something that's occluding my left eye more than my right eye's view, then that has to be accounted for in the matching process. We can also have specific features, and here square patches matches square patches, so in fact an area-based device is just a texture patch, but we can use edges, corners and zero crossings to do the matching process. If you remember from my example shown by David Marr, we were using zero crossings and it came up with quite reasonable results. The problem with edges, if you think about this when we were talking about motion and apparent motion, that a scene consisting entirely of horizontal edges or vertical edges of horizontal edges will not have any stereo disparity, but scenes with vertical edges will have stereo disparity, because if the cameras are horizontally separated, then you detect disparity in the X direction. If you want to detect disparity in the Y direction, you have to rotate the cameras around. The simpler the features, so edges and zero crossings being the simplest of features, we can have a problem with uniqueness, because there could be more than one edge in one image that potentially could match with a corresponding edge in the other image. Whereas that's less likely with corners and with texture patches. There was a trade-off in terms of simplicity of feature when computers used to be very slow, but now even our desktops are fast enough to do stereo disparity calculations probably at least 5 or 10 times a second, and as you know, these computers are not particularly fast. So here's what the disparity map looks like. Very well cited set of examples. Ogali and Eloimonos in 2005 showed how to do this disparity calculation, and you can see here these are the results. Now this is the result when you have a multiple pass algorithm. So the first pass tries to work out where the matches are, and then the second pass makes some assumptions of homogeneity and decides to merge targets that are within certain bounds to make them one distance. So you will see when you use the stereo algorithm, you will be asked how many depth bins do you want to place your results into. Do you want 256 depth bins? Do you want 16 depth bins? And then the results will be clustered accordingly. You'll also notice that there's a lot of noise suppression. There's not much happening around here. They are all at some cut-off distance, or there is no data. Like down here, the picture is too dark, and so we don't have any data down there. So it's only where you have some red hue that you can really count on the data. And here's an outside scene with some trees, and you can see here the target has been mapped such that the close object is a lighter colour than the other parts, and that we're getting reasonable matching across the entire picture. It's a very poor quality reproduction here, but there appears to be data everywhere around here, and you can see 1, 2, 3, 4, 5, 6 depth bins taking this ground perspective distance. So this is the sort of thing that you can expect. Now, if you verge cameras together, then the point of vergence, let's say the point of vergence is this, is a box being presented to a target, as a target to two cameras, and that vertical edge is the point of fixation of the towing in of both cameras. At that point you get zero disparity, so there's zero disparity, and then radiating out from there is the disparity given by textured areas on the left and right side of the box. We're not getting any matching over here and over here, and the algorithm falls over. So you can see this is the algorithm falling over here and here. This stereo verging facility we use an awful lot, and we use it because we are interested in the shapes of objects so that we can manipulate them, so we can pick them up. So our eyes verge in on a target to make sure that the bit of the target that's of interest to us is foveated, so this is on the central fovea of both cameras, both our eyes, that they overlap, and they give us the highest resolution where we are fixating. Now our eyes move around, so they saccade around the place, and at those points of saccades we gather three-dimensional detailed information so that we can interact with the targets. People are beginning to do that with robotic vision now, rather than just having two cameras. But there's a competing technique that I am not covering that uses active vision. So there's the Kinect camera, and there's another Sense camera just been released that provides an active vision system as well. So they have an infrared beam that is transit time is being measured, and they overlay that with the normal vision camera and add points of distance onto that camera source. So you will find that that type of new camera is possibly faster than using a stereo vision camera like this. I don't know what their prices are, so I don't know if anybody's using them.
Do you mean to say they actually use the data from the infrared sensor?
Yes. They merge them because they know the field of view of the optical camera, and the infrared sensor in the Kinect is off to one side, and it then the light is strobed across the field of view, and the echo that comes back is a modulated beam. The echo that comes back is timed, and that is then overlaid on, corrected for the measurement error, and then overlaid on the colour picture as a point cloud of depths. So there's two stereo techniques, but the one we're using is the passive one, which mimics human eyes and mammalian eyes. Now, I have mentioned Gabor filters, I think, earlier. They're texture analyzers. So a set of Gabor filters gives you a set of gives you a texture vector for a picture, or for a feature in a picture. So there'll be a Gabor output for this patch, and so on. You can see these are the Gabor values for this scene of a industrial robot. These are different Gabor analyses, and you can see here the textual information for these from the left and right camera views. And if you're using GPUs, then the Gabor filters are trivial to implement. Those who are using ordinary computers probably won't want to use Gabor filters. They're a little bit slow by comparison, but they give you a richer set of texture for comparing against than using corners, for example. I want to look at the OWL robot for doing stereo, and that means that you will be looking at Stereo Calib and Stereo Match, which are on the repository in my section. You can download those. We're going to be modifying the OWL robot slightly, the OWL code, so that we can save our calibration pictures, and I will make sure that we have 6 of these to hand so that we can do some calibration. Oh, actually, that's stupid. Each robot comes with a calibration pattern on it, so we don't need that. Okay, any questions on stereo? So here's some. I'd like you to just familiarise yourself with the principles here, and this is some of the code. You can see that after the calibration, we do a remap of the left source and the right source to be rectified. We then run the BM algorithm for stereo, or the SGBM. There's 2 techniques that give reasonable results in a reasonable time. You can see here we're setting some values up for the window size, the number of disparities that we're going to be worried about reporting, and thresholds for noise. And I'd like you to play with some of these parameters to understand how sensitive the stereo algorithm is to each. We then run the correspondence algorithm, which takes in the 2 rectified pictures and then produces a depth map, and we then normalize that depth map because it's a floating point array. We normalize that between 0 and 256 so that we can see the results on the screen. And that will produce something like this. So this is the data from the earlier paper. They've got a website full of reference stereo pairs that you can use for inspiration, to just check to see if your algorithm performs as well as you would expect. And here's the results. Now you can see this is not as smoothed. There are patches where there's no data at all. There's no data at the top, there's no data down the left, there's no data down the right. Wherever it's black, there is no data. The reason why there's no depth data around the neck here is because this section here can be seen from the left camera but can't be seen from the right camera, so it's shadowed. This is being occluded here. It's typical of stereo vision. This was done using the Python. Well, this was taken from the Python code. there's a lot of material on stereo vision, and some extra reading is from Forsyth and Ponce or from Boyle, both of which are available online. Okay, what I'm going to do now is to just go through some videos of computer vision in an industrial context, so that you can see how what vision can do and what the problems are. Sound here.
The four most common applications of the technology. So let's get started with a definition of machine vision. Machine vision is defined as the automatic extraction of information from digital images. So what exactly does that mean? Well, let's look at a very basic breakdown of a typical machine vision process. First, you have a manufacturing production line with a steady flow of objects. Then you have a camera or optical system trained on the line. Next, you make sure that you have proper lighting of the line so the camera can see the necessary details. The camera captures digital photographs and analyzes the images against a defined set of criteria. That's in an industrial context. There are different types of vision that are used for other purposes, but when we refer to machine vision, we're talking specifically about industrial vision as it's used in a manufacturing environment. Manufacturers use automated machine vision instead of human inspectors because it's faster, more consistent, and works for longer periods of time. Vision technology got its start in the 1950s, but the widespread use of machine vision in industry arose in the 1980s and 90s. This photo, taken from the Wikipedia entry on machine vision, shows a pioneering demonstration at a 1983 trade show of a system by Automatics, which is now part of Microscan. Of course, machine vision has come a long way since then, and is now used for many different valuable processes in manufacturing. Let's talk about some of the most common applications of machine vision. As it has developed, machine vision's applications have grown into four basic functions: measurement, counting, location, and decoding. Since its start, machine vision has been widely used for measurement, and by this we mean the automated measurement by a machine. That measurement can then be checked to a specified tolerance. For example, something we've been doing for years with machine vision is measuring the gap in spark plugs. As you may know, this gap needs to be a certain width, or the car won't run as well. Therefore, this gap measurement is an extremely critical spec for the part. We can use a camera and measure the spark plug gap by machine. This eliminates the need for a person to be there to measure and adjust the gap manually. We can automate the process and do it more quickly and accurately. Counting is another typical machine vision application. There are a few different tasks that fall under this category, but basically, Counting means to look for a number of parts or a number of features on a part. This allows us to locate missing parts and ensure that products are assembled properly. This example shows an aluminum flange with some holes drilled in it. If you count the number of holes, you'll see that there are exactly 8 of them. Assuming that we wanted 8 holes, we know that the drilling process was done properly. Another counting function is absence presence. Is it there or not? Here we have an 8-pack of sodas, and you can see that one of the sodas is missing. With machine vision, that packaging can be checked to make sure an incomplete pack doesn't make it to the grocery store shelf. We've slowed the process down so you can see it, but machine vision systems can operate much faster. Location is when machine vision is used to report the position and orientation of a part. This may be done for several reasons. We can locate the position and orientation, and then check that to a specified tolerance. So, in other words, you're looking at the part to make sure that it's at the correct angle, and using that as a reference point to verify proper assembly. You can also use this for alignment to other machine vision tools. Let's take our spark plug example. This is a very powerful feature in machine vision. Your parts may be facing all different directions as they go down your production line, and you can locate a part, straighten the image, and then you can run other machine vision processing tools on it. Additionally, you can find a unique pattern and use that to identify a part. An example you can see here is a can of soup. The vision system has been trained to look for a pattern on the soup. In this case, the portion of the label that says tomato on it. We can use that pattern to verify that we do, in fact, have the right soup going down the line. Decoding refers to the decoding of 1D and 2D symbologies, such as linear barcodes, stacked symbologies, as you see here, and 2D symbologies, such as data matrix codes. This also refers to OCR, or optical character recognition, which is text that is simultaneously human and machine readable. Decoding is typically used to record information as historical data. That way you have a record of parts that have gone through a process. You can track the path that a part took through that process and use that data for immediate action, meaning that you can look at the data and sort based on what it says. You can also validate the data for correctness. When you read a marked code on an object, you can verify that the data in the mark is correct, or that the format of the data is correct, or that you have the correct product going down a production line. An obvious question here is, why use machine vision to do this, when dedicated auto ID systems would do the same thing? You might think of machine vision as auto ID or barcode reading plus. The plus is the ability to run other measurements and operations in combination with the reading of barcodes or text. For example, you might want to read a label and also check that it's properly aligned to the product. In other cases, you may need the ability of a machine vision system to tackle tougher applications that require more capability in terms of image pre-processing, or in the case of a PC-based system, sheer speed and processing power. An example of this sort of application is reading the OCR code on a can of vegetables during a high-speed canning process. You may not realize that when vegetables are put into cans, they are usually done so with no labels, and the only indication of what's inside is a text code on the end of it. When the time comes to put the label on the can, a vision system checks the code on the end of the can to make sure that the right vegetable is inside the can and matches the label. So, let's review. Machine vision is the automatic extraction of information from digital images. And we talked about the common manufacturing applications of machine vision, which generally fall under 4 basic functions: measurement, counting, location, and decoding. The visual examples we've shown you here are mostly slowed down so you can see what's happening. In reality, machine vision can operate much faster, processing hundreds, or in some cases, even thousands of pieces per minute. But that's just one of the many reasons manufacturers are using machine vision. be sure to check out the next installment in our series, Why Use Machine Vision, where we'll take a look at the benefits of this technology.
Luckily we have
Welcome to Microscan's Introduction to Machine Vision, an educational webinar series to help new users better understand Floor. I'm going to talk about 4 ways that machine vision can help manufacturers save money, and why this automated process is better suited to repetitive inspection tasks than human inspectors. If you tuned into our previous presentation, then you already know what machine vision is, and its 4 most common applications: measurement, counting, location, and decoding. You might use these tools to achieve a number of different ends, but the motivation for doing so is generally like all others when you're applying industrial processes: to save money and increase profitability. Thinking in these terms, machine vision accomplishes this in several ways: by reducing defects, increasing yield, tracking parts and products, and facilitating compliance with regulations. Machine vision inspection can reduce defects, or cause what we'll call fewer catastrophes. Fewer bad parts getting out into the world and into customers' hands, which could damage a company's reputation and lead to costly product recalls. Along those lines is preventing mislabeled products, parts where the label doesn't match the content. Mislabeled products create unhappy customers and have a negative impact on a company's brand. They may even pose a safety risk. Consider the consequences of improperly labeled pharmaceutical products or mislabeled food items for customers with allergies. This is a very common reason for product recalls. Machine vision can verify contents and ensure that products are labeled properly. Here's the label matching application we showed you in our last presentation, where we use machine vision to read the 3-letter text or OCR code on the top of a vegetable can to match it to the correct label. Another incentive for machine vision is better yield. Simply the ability to turn more of the input material into saleable end product. If you catch defects early in the production process, you'll reduce waste, because bad parts can be identified and eliminated before they're built into larger assemblies. You'll avoid scrapping expensive materials and reworking parts. This image shows a molded lead frame, an electronic part that our vision system is measured to detect any deformation. By detecting defects at this stage, we'll avoid having to scrap larger assemblies later on in the process. Machine vision helps to reduce downtime, another benefit that falls under this category. For example, a packaging line may use a vision system to detect product misfeeds that could cause the machine to jam and result in downtime and loss of product. In the case you see here, a vision system is ensuring that these baked goods are properly aligned as they travel down a conveyor. Items that are out of tolerance will be expelled from the line before they can cause a system jam. I'm sure you're aware of the usefulness of tracking work in process, or WIP, uniquely identifying products so that they can be tracked and traced throughout the manufacturing and stocking process. Machine vision can be very helpful here. Typically, if you can identify all of the pieces in a process, you'll require less stock, and product becomes available more readily for just-in-time processes. Machine vision uses decode tools to read 1D and 2D symbologies, as well as OCR to track parts and products. This helps manufacturers to avoid component shortages, reduce inventory, and shorten delivery time. This is also where the Auto ID Plus aspect of machine vision can be beneficial. Of course, track and trace applications such as this are commonly accomplished with dedicated barcode readers or imagers. Machine vision provides the added benefit of being able to perform other tasks such as alignment or measurement, in addition to reading barcodes and OCR. As an example, you may want to read a data matrix code on a PCB and also verify its location on the board. Complying with industry regulations is often an unavoidable cost. But if you don't comply with the regulations relating to a particular product, you may not be able to take part in that market. Being able to do so efficiently and at low cost is clearly beneficial. The pharmaceutical industry was an early adopter of machine vision for this reason. It is, of course, a highly regulated industry and requires strict adherence to government regulations to ensure product integrity and safety. A common application we see here is the verification of lot, date, data matrix, and other code formats, a requirement for compliance with standards such as 21 CFR Part 11 and GS1 data standards. Unlike a dedicated barcode reader, a vision system has the capability to not only read the codes, but to verify that the labels are printed accurately and legibly, ensuring that they are readable later in the supply chain. There's also the broader question of, why use automatic systems like machine vision to do things that you could potentially do with human inspectors? The answer is, quite simply, machine vision systems never get tired. They excel at repetitive tasks. Once they're set up to do an inspection, they will do it all day, every day. Whereas with human inspectors, you would typically expect to find an error rate going up after about 20 minutes on a particular task. Machines do it faster. You can inspect things more quickly with a machine. The other great benefit is consistency. Once the rule is set, it's set and will stay set. People who are inspecting or operating a process have a tendency to change the rules as they go along. So that should give you some pretty clear justification for using machine vision. Let's review. Machine vision helps manufacturers increase their profitability by reducing defects, increasing yield, tracking parts and products, and facilitating compliance with regulations. We also compared the benefits of machine vision to human inspectors. Machines are faster, more consistent, and can run for longer periods of time. With so many compelling reasons to incorporate machine vision, you're probably ready to learn what you'll need to put.
So, just the last one.
Welcome to previous presentations. Then you're already familiar with some of the applications of machine vision and the benefits it brings to the production process. There are typically 5 components that make up a machine vision system. They include the lighting, lens, sensor, vision processing, and communication. Here you can see 2 examples of different types of machine vision systems. On the left is a system made up of assembled components, which includes a PC and a camera, along with external lighting to illuminate the part. On the right is an integrated system, or smart camera, where all of these components are built into a single device. Choosing the right configuration depends on the requirements of your application. Lighting is a critical piece because it illuminates the part to be inspected, allowing its features to stand out so that the camera can clearly see them. Next, you have the lens, which captures the image and presents it to the sensor in the form of light. The sensor in a machine vision camera converts this light into a digital image, which is then sent to the processor for analysis. Vision processing consists of algorithms that review the image and extract required information. Then the system will run whatever measurements or other processes it has been instructed to run. Finally, the resulting data is communicated out to the world in a useful manner. Before we take a closer look at each one of these components, it's important to note that the part itself is a consideration. How will the part be presented to the vision system? Part placement and orientation should be consistent and repeatable to achieve the best possible results. Proper lighting is critical to the success of an application. The type and position of a light should be carefully selected to maximize contrast of the features you plan to inspect and minimize contrast of everything else. This is like an electrical engineer setting up a system to give a high signal-to-noise ratio. You're trying to make the pieces you need to see, or need to measure, very clear, and you want all the other items in the image as invisible as possible. To give you an idea of how you might do this, let's look at some examples. Here are two photos of the same light bulb, and let's say that the objective is to see the tungsten filament between the two conductors. In the image on the left, the light is between the camera and the part. On the right, the light is behind the part, away from the camera. In the front lit image on the left, it's quite hard to see where the filament is. But in the backlit image, you can clearly see the filament, making it very easy to check its presence and position. In this case, the light's position is critical. Here's another instance where the position of the light impacts the image significantly. In these images, the same part is lit with the same light. On the left, the light is placed near the camera lens. In the image on the right, the light is positioned lower and closer to the part. This clearly makes a big difference in the way the data matrix code shows up, as well as the outline of the part. This pair of images shows foil packaging with a printed expiration date. The light is positioned between the camera and the part in both instances, but a different type of light is used in each case. The example on the left is lit with a ring light, and clearly you would have a tough time locating, let alone reading the text in the image. The right-hand image, however, shows the same part lit with a dome light. You can see how dramatically the lighting changes the appearance of this part. In this case, it's the type of light that affects the image. If you can't see the necessary feature on a part, you can't measure it or read it. Proper lighting is key to acquiring a quality image with clearly visible features. Next, we'll discuss the lens. The purpose of the lens is to capture the image and deliver it to the sensor. The lens will determine your field of view, depth of focus, and your focal point. Generally, you'll find one of two different lens types in a vision system: an interchangeable lens or a fixed lens. Interchangeable lenses are typically C-mount or CS mount. The right combination of lens and extension tube will acquire the best possible image. A fixed lens is part of a fully integrated smart camera. Fixed lenses typically use autofocus. This could be a mechanically adjusting lens or even a liquid lens, and it will automatically focus on the part. Autofocus lenses usually have a fixed field of view at a given distance. Lens choice can dramatically affect the appearance of an image. Here are two examples that were taken with the same camera using different lenses. The image on the left was taken using a 12mm wide-angle lens. This lens provides a larger field of view and less magnification than the image you see on the right, which was taken using a 25mm lens. If you use a lens with a longer focal length, you will magnify the image and reduce the field of view. The lens delivers the image to the sensor in the form of light. The sensor typically uses CCD or CMOS technology to capture this light and convert it to a digital image. When you zoom in on this digital image, you can see that it's a collection of pixels. Low light produces dark pixels, while bright light creates brighter pixels. It's important to ensure your camera has the right sensor resolution for your application. Here's an example of the same image captured at different resolutions. On the left is an image captured with a 0.3 megapixel sensor, also known as a VGA sensor. On the right, the same image is captured by a 2 megapixel sensor. You can see that the image on the left has much less resolution and is more pixelated. The higher the resolution, the more detail an image will have, and therefore the more accurate your measurements will be. The size of your parts, tolerances, and other application parameters will dictate your required resolution. The next step is vision processing. The processing function is truly at the core of machine vision, the mechanism for extracting the information that is required of an application. Processing the image may take place externally in a PC-based system or on board in a smart camera. Vision processing is performed by software with a wide variety of interfaces and tools available. Some common vision software tools include locate, count, measure, and decode. Tools are often used in sequence to achieve a desired result. A typical example of this is an inspection application that uses a locate tool to locate a cap on a bottle. The measure tool then measures its height to ensure that it's properly seated on the bottle. Vision processing consists of several steps, or algorithms, performed by the software. First, the image is acquired from the sensor. In some cases, pre-processing may take place to optimize the image and ensure that all the necessary features stand out. The software then finds the features that it's supposed to look for, runs measurements, and compares these to the specification. Finally, the results of these measurements will be communicated as pass or fail. This brings us to our fifth component, communication. As discussed earlier, the purpose of machine vision is to extract useful information from digital images. The communication of that data is critical. Typically, this is done by either a discrete I/O signal or data sent over a serial connection to a device that's logging information or using it. Many smart cameras have these connections built into them. Discrete I/O points may be connected to either a PLC, which will use that information to control a work cell, or an indicator such as a stack light, or directly to a solenoid, which might be used to trigger a reject mechanism. Data communication via a serial connection can be in the form of a conventional RS-232 serial output, or Ethernet. Some systems employ a higher level industrial protocol like Ethernet IP, which might be connected to a device like an HMI screen, as shown here, to provide visual confirmation that the system is running. Let's look at how these different parts work together to create a machine vision system. In this example, we are inspecting the fill level and cap alignment of water bottles. We'll begin the process by triggering the inspection when the bottle comes by. This will trigger the lighting to illuminate the bottle so that the camera can clearly see the necessary features. The lens and sensor will then capture and create a digital image and deliver it to the processor, which in this case is a PC. The software platform running on that PC will extract the required measurements to ensure that the fill level is correct and that the cap is properly seated on the bottle. The current status of this process can be communicated to and viewed on an HMI screen. Other actions may also take place based on the results of the inspection. So let's review. Machine vision systems may be integrated, such as a smart camera, or they may contain multiple components, such as a gigabit Ethernet camera solution. The 5 key components are the lighting, lens, sensor, vision processing, and communication. Lighting is critical to the success of a machine vision application and should make the features you're going to inspect stand out. The lens captures the image and delivers it to the sensor in the form of light. The sensor converts the light into a digital image. The processor uses software algorithms to extract useful data from the image and determine the results of the inspection. These results are then communicated in a useful manner. If you missed the previous presentations in this series, you can find them on our website at www.microscan.com, as well as additional machine vision resources including white papers, case studies, and videos. Thanks for watching.
So that's the gist of industrial inspection. It's got all the key components in it, and I hope you can see how the things that you've been looking at fit into that structure. We are kind of towing the line between learning about industrial vision and doing things that are more cognitive. So the emphasis on stereo and other tools, certainly OpenCV, are there because there's more to industrial inspection than has been shown there. If you want to inspect a bottle for the presence or absence of a lid, for example, that's very straightforward. If, however, you want to inspect a tray full of lasagna to decide whether in fact it's got all the right components in it before you put the top on it and then send it off to Marks and Spencer's, you need quite a different set of intelligence in your computer vision software. So machine vision is doing a lot of things for mass production. It's only just moving into food inspection and only just moving into agriculture. And I think you're probably already familiar with Martin Stolin's Gumi robot. The vision system that goes with that has been demonstrated in the laboratory, but actually getting it running outdoor in the field is a major challenge. So that's the future for computer vision systems, is actually making machines that can do these tasks under resilient lighting conditions. That's partly due to how you control the illumination, partly to the type of camera that you're using, and partly due to the processing that you're doing subsequently. So I'll talk next week briefly. I'll walk through an example, making specific points about measurements, things that you have to know about. But for the rest of today, let's just get back to doing some software. Now, I'm quite happy to have a break for a few minutes if people want to do that, but I want to come around and I want to see where you're at with your understanding of computer vision, and I also want to talk individually to you about your thoughts on your mini project. Thanks.
Oh, yeah, thank you, myself. Είχα αποφασίσει τι θα κάνεις.
Δεν έχω ιδέα. Δεν έχω ιδέα. Δεν ήξερα τι να διαλέξουμε τώρα.
Ναι.
Δεν ξέρω και τι project να... Δεν ξέρω καν δηλαδή τι requirements έχουν τα project. Δεν θα το ρωτήσω τώρα. Θα μας μιλήσει. Έχεις πάρει κάρτα? Όχι, δεν έχω. Την κολλητή σου δεν τη βλέπω πολύ ωραία σαν τις τελευταίες μέρες, δεν ξέρω τι έχει πάθει.
Με χαρά.
That's not that one. It's got that. It's not this one. This one has that.
Hasn't that one got like little wing bits that come off it? That mount has got little bits that stick out.
Right, that's fast.
Good.
Right, I'm going to grab some edge detection. Okay. Let's just get that started.
Yep.
I haven't submitted anything yet, but my idea for a project was to do something along the lines of geometry in a room from lines and trying to find a conversion point on the horizon. And so I estimate the horizon without being able to see it.
Right, that's interesting.
Yes. Because I was just looking at this like YouTube videos of art, but the horizon, I think it's what's called light translated to source of inspiration. So don't know how well it would work, but obviously it depends on things actually being complicated with gravity. Obviously redundant compared to accelerometers, but something a bit different.
Yeah, no, that's very interesting. It's very interesting. Okay, good. That's acceptable.
But what would be like the major challenges?
Well, rejecting information. I've got a picture. It sounds to me that you're going to edge detect that picture, and you are then going to process it to look for perspective distortion or convergence lines. So getting a set of test pictures would probably be important for that. There may not be enough information in the pictures, although you will clearly see there's information in there, but the machine won't be able to find that. It's probably something that will work with a pyramidal encoding, so you take a picture and then you'll reduce the resolution of the picture so that you have a rather low resolution picture, and the orientation and lines in that low resolution picture with the gross artifacts of perspective. It's probably like that's present in that picture. It's also worth looking at those keywords to see if other people have implemented a system that does that. It's perfectly acceptable for me to implement something that somebody else has done. Of that complexity. Just saying you're going to do a Hoff transform just by copying somebody's Hoff code is particularly challenging. But looking at perspective is interesting. Possibly challenging. See how you get on. If it becomes difficult, because I don't know anything about this area at all, then we'll think again. But we'll try and think of gathering some test pictures.
Yeah, some sort of like the Eiffel Tower group,
yeah, possibly, yeah, shots of streets or railway pictures.
Yeah,
street scenes where pavements converge, things like that.
Is there something on the DLE, like a template for this?
No, it's free form. Alright, just what do you need to do? Right, the specification is that it's very wide. It must be something that you feel comfortable doing. It's got to be machine vision. If your master's project has a machine vision component in it, then you can use part of that as your mini project to just sort of get you into that component. No, well there is. If you look at the introduction, where I talk about overview, there's a summary of it in there. And if you look on the DLE, in fact, you go back to lectures, so go up from lectures, and you'll see there is mini project. I can tell you there. I'm not going to talk to you. We're sorted, unless you want to talk to me. Yeah, good.
We're looking at see because it's like happy with how things stream down from the app ready to see, so it's a place to see the light.
Oh, okay. Right. When you need to understand how to read NJPEG into Python, I think it's trivial. You just need to set up a video object. It will automatically, you can probably use almost the same line of code, and then we can run. Video capture, that object, look video capture up in Python. OpenCV. You're doing it in 3.1 at least.
What did you do with it? What was it last year?
Yeah, CV2 video capture will work. So you should just be able to replace video capture capsules with CV cap equals CV2 video capture brackets and then a source string.
That's one that actually talks to it.
Yeah. Now that's more complicated. You didn't ask me about that one. You were talking about video. Okay, you need to look up sockets in OpenCV in Python, and in fact, if you look at the source code that is in the our user guide, you'll see there's some Python that creates the receiving socket for. There's no sources in there when you're looking at it. You need to look at the code and go right back to the beginning. It's in the early setting up. Here's Python code for there. Socket equals socket.socket host port socket bind. Those are Python commands. And here you're doing a listen and listening, but in fact you can do a talk. I'm not sure what talking is in Python, whether it's send or transmit. If you look up socket TCP sockets, you'll be able to replicate
That's
that.
the code that's in the hour already.
Yeah. So you can make similar code that does the reverse, the other way. Yeah, send. That's true. What about mini project?
Well, we just talked about this. How thinking about object tracking.
Yeah.
Did you build your?
Yeah.
Is that build your object challenging enough?
It's challenging enough, yes. Alright. So you want to use the hour?
Yes.
Okay. Well, you can make a bee in your bonnet about something. Some people do. I had one guy who wanted to do an industrial inspection, and he got some pictures of, you know, we saw on the video there, the tops of cans and the printing on them. He took pictures of them, demonstrated a system, and now he's working for a machine vision company. So that was a single camera. It's all useful. Actually, if you go for, I haven't said this here, but I teach the OWL in a bit more deeply in with my final year students, and this last year, 6 of them have got excellent jobs with military and international companies doing specifically machine vision, and they got it on the base, on the back of learning OpenCV, doing stereo tracking, convergence control. I'm more able to talk knowledgeably about that. So there's plenty of jobs out there.
Quick question on, it's actually my project. I'm currently working with Martin on the Raspberry.
Oh yes.
So we're going to have a single video and depth sensor.
Yeah, I can't remember what that's called, the one he's buying.
Yes, yeah, good. I've got it now, just in that case. Building the actual sensor.
Yeah.
I just wanted to, for the purposes of is it, would you mention about assigning values to each pixel from the depth sensor?
It's called a point cloud.
Yeah. Would you keep them, is there any benefit in keeping them separate, so one cloud and a VGA, or merging them immediately and dealing with it like that? Would there be any?
Depends what you're trying to do. You can use the point cloud to reject information from the VGA camera, or from the HD camera. So you can kind of make decide an upper and lower bound on distance, group points within the cloud around those distances, or rank them in order of distance, and then use those to remove or zero the processing everywhere else, so the picture then just becomes black except where you've got important bits. Then you can ask questions like, I've got this blob here. You don't actually need to zero it all really, but you just say, I've got this blob here that's close to me. I can fit a bit of a raspberry-shaped sphere model over that, and depth terms. Is it the right colour? Or is the colour strong enough? Is it saturated enough to tell me it's the right one? So,
initially, I've only got because I haven't got the data and the new sensors. I've only got some normal pictures.
Yes.
To work on.
Yes.
I've got to do ground truth for those.
Yes.
Ground truth
Get the ruler out. I'm serious.
Cool. That's going to be fun.
A piece of string. Anchor one end, the midpoint on the camera, and then measure the other one, and then measure the other end. It's laborious,
Yeah.
but it has to be done. I'd also counsel against you jumping straight into doing things with neural networks until you understand what you're doing and what the data's telling you.
Oh yeah, that's the end goal. I'm not going straight into that.
Good. Yeah. Oh, yeah, that's it. What are you doing?
Trying to get communication.
Yeah. No, for your project.
Oh, I'm doing the same thing.
For your master's project.
Monitoring attention to progress.
Oh, okay. Cool.
So we've got several
People looking all over the place. Yeah. Good. So what are you going to do project? How have you been getting on with the software? which pieces of code that we thought were useful and trying to understand.
Τελικά τι θα κάνεις?
Εγώ είδα αυτό για το στο...
I guess if you could have it so
Have you been going through some of the ones that I asked you to look at?
like track
Threshold. Okay, well that's alright, as long as you...
maybe
You do it here. Okay, that sounds a sensible thing. What are you doing for your master's project? Oh, okay. Right.
Εγώ την κουβάρια γιατί την άνοιξα.
Let me suggest that you do a coloured object tracking activity. So you do the processing to be able to track an object, and also to some coloured object on the computer. So you need a webcam or an owl. An owl will be the webcam if you need it to be. And you estimate distance of the object.
Θα κλέβει.
Έλα.
Δίνει εύκολα στους υπόλοιπους. Εμάς θα μας δώσει.
Yes, that's right. Yeah. Well, no, by limited set objects based upon the size of the object. So you know how big the object is, and you develop a system that can track the object up to 5 meters away. So it just tell you where it is in the object.
No, the contrary. Oh
So
lord.
that's the tracking system. Yes. So for that you need to focus on if you look for a keyword, so just go back up here, click on that and type in OpenCV. Coloured object tracking. Coloured, yes. Object tracking. Do you prefer Python to C or do you prefer C?
Δεν υπάρχει πρόβλημα, ότι θέλεις να το κατεβάζει το αστέρι. Αβαγίδα. Το source τι είναι? Ρε φίλε, έχω ένα προβληματάκι. Το image, ξέρεις τι δεν μπορώ να πάω. Δεν μπορώ να... Από πάντα έχω αυτό το πρόβλημα. Υπάρχει ένα... Έλα εδώ κοντά. Ούτως άλλως το γράφω εδώ. Λοιπόν, κοίτα. Βλέπεις εδώ πέρα, μου βγάζει πρόβλημα στο image. Αυτό δεν το χρειάζομαι ούτως άλλως.